again, welcome to the Environmental Express Third Thursday webinars. My name is David. I'm the technical director here at Environmental Express, and I've been doing these for a while now. Really enjoy it, and you guys are the ones who make it worth us putting these on. Hopefully everyone gets a little something out of it and comes out, and we all come out a little bit smarter. I'm going to start this one off with a special emphasis of I am not an auditor. I do not certify you for any of your tests. I do not have the final say in how things are run and how you need to do it in order to make it work. I merely present my experiences and my interpretations of the regulations as I see them. If what I say is in direct contradiction from direction you have from your SOPs, your QA officer, and especially from your assessor, most likely their opinion is of more importance than mine, and you should follow that. You may use the ideas that I present to try to discuss a compromise between what you think from what I say and what you're instructed. However, those people in particular have the final say over what you do and how you do it. All right, all the niceties out of the way, so let's get started. Let me minimize my control panel here, get this guy out of the way so that I can see everything that I need to see. Move that, we'll move that, and there's my hide. Okay, all right, so how to comply with temperature monitoring requirements. I really liked this picture. Our creative team asked me what I wanted. Y'all probably saw this in your email invitations. Those of you who are in charge of QA, maybe you've looked like this guy before and had all of these thoughts, probably not in actual pictograms for your thought bubbles, but yeah. So we're going to talk about lots of different things in relation to temperature monitoring. Why we do it, where we do it, how we do it, how we manage to mess it up. That's not a specific slide. That's going to be addressed kind of throughout things. And then some examples of different areas in your lab, different places where you may need temperature monitoring. I'm specifically going to pull examples from certain methods and discuss how they relate to stuff, to various things. Start with the boring stuff. This is the second, the previous slide, it was the first, and this is the second one where I've only got text, so we'll get the two boring ones out of the way, and then we'll have some fun pictures throughout the rest of it, I hope. I think I do. I'll have to double check. Why do we monitor temperature? There are two simple answers. We're told to, and it makes things work. So we've got regulations for sample storage and transport, doing your daily temperature records, showing that you are compliant with methods. It's interesting how your assessors rarely are concerned about the performance of the method as much as are you following the method. But that's a whole nother topic. And then, so that's because we have to, that's the administrative part of monitoring temperatures. And then there's the actual practical part of monitoring temperatures. And sometimes the temperature actually is important for your test to work. Your distillations, your microbial growth, all of your microbiology testing, drying things, doing digestions. Any of you who happen to do volatile portions of your gravimetric solids analysis know all about your ignition temperature. Or if you happen to be lucky enough to do a BTU or an ignitability test, that temperature monitoring is a very important part of those processes. There are probably other reasons to monitor the temperature, but these are the two main ones, and they're probably the most relevant to us and what we do on a daily basis in our job. Where are we monitoring our temperatures? Wow, I just realized that the top right picture is white on white, and it's really hard to see. It looks better on my other monitor. That's a refrigerator type incubator, for those of you who may not be able to really see that top right image. That looks just like a couple of lines right now. But we've got, the sample storage, sample transport, that we've got a microbiology type incubator. We've got digestion blocks. TCLP, I remember the first time I learned about TCLP was, it was not done in the department that I worked in, but I heard about an audit finding where the temperature was not monitored for our TCLP rotators. So we had to get a conditioned room where we could monitor the temperature constantly. Distillations, lots of different pieces of equipment, lots of different places, lots of different types of things that we need to monitor our temperature in. The different places kind of lead into how we do the temperature monitoring. Everything that you end up doing with your temperature monitoring needs to come back to, if you see the image on the left there, I hope that paperwork behind it is somewhat visible. We've got a NIST traceable thermometer. So every temperature monitoring that we do has to eventually be traced back to a NIST reference of some sort. Most of you, probably your QA officers, have your, they've got a NIST traceable thermometer in each of the appropriate ranges depending on what you're monitoring, either the sub-freezing temperatures, the refrigerated temperatures, the approximately ambient to a little warmer than ambient temperatures, and then the really hot temperatures, boiling and above. So usually they've probably got those kinds of ranges, and they've got special NIST thermometers that cost a lot of money, and they're probably kept under lock and key so that none of us clumsy analysts get our hands on them and accidentally break them. And then all the other thermometers that you're using throughout the lab are checked against those thermometers, those NIST thermometers, on a regular basis. It may be annual. I think it's at least annual for everyone. I know you may do more regular checks on those as well. When I was in the lab, the last time that I actually had hands-on experience doing these, those NIST thermometers, the liquid in glass type, I think that's what they're called, thermometers, were the one and only standard that you could use. Since then, I know there have been several options brought with NIST traceable digital type thermometers, and those things may be of use to you now. They do offer some benefits, a lot easier to read. You don't have to worry about graduation lines and misreading what your scale is. They've got a clear, concise readout, and even better these days is that a lot of your digital ones actually offer some tracking capability and recording of your information. We'll get to that again a little bit in, I think, the next slide after this one. Your regular liquid in glass thermometers, there's a couple of types, and this was something that I learned also during an audit response, I think, at one time, when one of the findings was that the temperatures were not being taken correctly, and that the temperature compensation was not adequately addressed. So one thing that they found was that we had a partial immersion thermometer in use in an incubator. So when you're taking temperatures, you can either take the temperature of an object, or you can take the temperature of the surroundings, the environment in an area. The best example of that is in an incubator or an oven versus taking the temperature of a sample. So the incubator or the oven is an environmental temperature versus a sample is a specific object temperature. And so partial immersion thermometers, if you look at the image on the top, let's see if I can, let me get my pointer tool out right here. So this line that's indicated on this thermometer is the immersion line. And with a partial immersion thermometer, what you are supposed to do, as you see down here in this middle image, you can kind of see that line there. You are supposed to immerse the thermometer to that immersion line in the liquid that you are taking the temperature of, or maybe solid if you've got, you know, grains of sand or something along those lines. But you're supposed to immerse the thermometer just to that line. And it makes a difference because the actual thermometer itself has some measure of expansion and contraction based on the temperature that the thermometer experiences. And so it is calibrated to, so that that line is taken into account the expansion of the thermometer itself. I've never actually used the picture on the left, the total immersion thermometer, where it's designed to immerse the thermometer only to the level of the, in this case, the mercury column. Sometimes it may be an alcohol column or whatever the liquid in your thermometer is. So you're only supposed to submerge the thermometer up to the level of the liquid that is indicating on the scale. That one actually requires you to have some knowledge of where the temperature is going to be and then slightly adjust the thermometer as you get a final temperature reading so that you have it done. And then the complete immersion thermometer, that would be one that you would use in an oven or an incubator of sorts, and that is supposed to have the entire thermometer exposed to the temperature that is being recorded. And again, this is all so that the thermometer itself does not contribute to any errors in the actual measurement and reading of the thermometer. So what we had was we had a partial immersion thermometer in use inside an incubator. And it was ignorance on our part that the distinction existed and that there were different ways to use them. I think the previous group that had been in charge of that, this had been shortly after some turnover, and so they had been aware of it and had done it properly, but that type of information had not been communicated to the next group that came in to do that. And then when a thermometer was replaced, we just got the wrong one because we did not know that there was a specific type to acquire. So check your thermometers. Make sure you're using the correct type of thermometer, and if it is a partial immersion thermometer, make sure that you have it inserted to the correct level when you are using it. Recording those temperatures. So again, back in the day, your manual logbooks here on the left. Just a simple writing down of the temperature, you know, who did it, when it was done, the day, the time, the actual recording, any notes that you may need to make on it. I think a lot of us have used these and probably have mean thoughts about them at some point of our job and wondered, man, I wish there was some better way to do this. There is pending your particular program area requirements. This is the cool thing. So the control company is a sister company of ours. They are also part of the Cole-Parmer group. And they have some really cool products that they are starting to roll out there. This top one is part of the Traceable Live series. And these are Bluetooth-enabled electronic temperature monitors, electronic thermometers. And they do a continuous reading of, actually I guess they're more than Bluetooth, they're actually Wi-Fi enabled. They do a constant reporting of temperature, so you set them up for the frequency to be monitored, and they report on whatever basis you tell them to the cloud, and all the temperature data is stored, and you can set it up with apps to smartphones or tablets or computers, depending on who needs to know about things. Alerts and alarms about when things approach warning limits or have exceeded warning limits. And then it's a continuous thing that can always tell you if your samples are in control or if your storage is in control. And that's a really cool function. And then the bottom picture here is something that I actually had not heard about until I was looking at it today. And I think it's really, really cool. This is called Traceable Go. And these are just, they're about the size of, I don't know, some of those step trackers that you would attach to your belt. Old school, back before we all had our wristbands and smartphones that did it for us. But these are just portable temperature loggers that you could, for example, throw in a plastic bag and put in your cooler of samples and ship that back to the lab in the cooler, and it would do a continuous monitoring of the temperature in that cooler while it is turned on. So you've got the start-stop button there. You can see, so you press start, throw it in the cooler, and it starts recording temperatures. And then you bring it out and you press stop, and then it's got Bluetooth connections to the same type of app as the Traceable Live, and it will then download the temperature records for that period that it was active. And you can use that as temperature compliance type processes for your sample receipts. I really, really like that concept. I think it's a lot of fun. So that's how we're measuring our temperature. Was that, did I skip? Nope, that is the right. Okay, we're in the right way. So now let's talk about some examples, some things that we may encounter in our lab, some spots where we're asked to monitor temperatures. Hot block digesters. Metals digestions is typically where these are used, although I've seen phosphorus digestions, I've seen people doing, I guess mercury is still a metals digestion. So there's a couple different things. Hexavalent chromium, again, still a metal. But I've got here the requirement out of the method that talks about the temperature. Tells you to add some acid, and then what's that, the third sentence, the hot plate should be located in a fume hood and previously adjusted to provide evaporation at a temperature of approximately, but no higher than 85 degrees. Now this is one of my favorite wiggle room statements, where it says approximately, but no higher than. So a lot of times we'll have temperatures where we say 35 degrees plus or minus a half a degree. Well, this one, and so we don't have to have it exactly 35.00000, etc. At all times. We get a little bit of wiggle room on our temperatures because control mechanisms do fluctuate slightly in how they respond. So this one, we're allowed approximately 85, but no higher than 85. What is approximately? What does that mean to you in your lab? Is 80 approximately? Probably not. Is 82? Maybe. Is 83? More maybe. 84? I would say that's approximately. 84 and a half, that's definitely approximately 85. 85.1, that is still no higher than 85 because it just says 85. 85.6, that's actually 86, so that is higher than 85. So there's all sorts of interpretations there in that approximately, but no higher than. And then it also talks again about later on in the method, you'll put the watch glass on. You don't actually change the temperature of your hot plate or hot block to raise that temperature to 95, but you just cover it with the watch glass. And that increases your vapor pressure enough to bump the temperature up about 10 degrees to get to approximately 95 degrees. So the question then becomes, 85 or 95 degrees C, is that your block temperature or is that your sample temperature? And what it's actually asking for is for your sample temperature to be 85 or 95 degrees. And so what temperature do you set your block at in this case? Well, the answer there is not 85 degrees. Because, and without getting into all of the physics of heat transfer, if you took your thermodynamics class back in college, you may be having some nightmare flashbacks now. But anytime you transfer heat between a medium, between two different media, you get some heat loss. And it all varies depending on the contact efficiency and the heat transfer efficiency. And there's some coefficients involved in all this. It's a fun problem if you have all the proper equations and all the proper data, but there is actual heat loss. And so you actually need to set your heat source higher than what your sample temperature needs to be in this particular case. And that's because we are not heating the environment, we are heating the sample in this case. And so what we typically tell our users with our hot blocks is you want to shoot for a block temperature of 20-ish, maybe 25 degrees higher than what your target sample temperature is. And that's because you have to heat the block, and then the block has to heat the sample. Unfortunately, you don't have direct contact between the block and the sample. You have to go from the block through the plastic of the digestion vessel. However, you don't actually have a perfect contact between the plastic cup, the digestion cup, and the block itself. We can't make it exactly flush because then you wouldn't be able to put the cup in. You'd get air lock and never be able to push it all the way in. And then if you were able to put it all the way in, you would not be able to pull it out because you would create a vacuum underneath and you would not be able to ever remove that cup. So there is an actual air barrier around the edge of the digestion cup between it and the block. So you have to heat the block, you have to heat the air around the cup, then you have to heat the cup, and then you have to heat the sample. All of those transfer steps of heat involve heat loss. So your block temperature actually has to be set at 105, 110, 115, somewhere around there, in order to get your sample temperature at the correct level. So then what do you do? How do you check this? Well, you need to have you need to monitor the actual sample temperature. Some of you may have been asked to monitor the temperature of each individual spot on your hot block. And you may have constructed some charts. We've got one, this is probably a decade at least old, that we put together. And this is just spots that kind of map out edges and spots and middle and corners and things of one of our 36 well hot blocks. Just to kind of document some of the temperature across that block. And I debated actually putting those tenths of a degree on there, but I figured why not. So our average there across all those different spots was 95.08 with a standard deviation of 0.77 degrees. So it's a very, very consistent block. And as we'll see in the next picture, there's a reason for that. So those of you who have done maintenance on our blocks on your own may have seen this already. This is just the graphite out of a block upside down, and that orange you see is our heating element. So as you can see, it is one solid block with a heating element underneath it. It's applied evenly across the entire surface of the block, and it's an all or nothing thing. You can't just heat one well. You can't just heat part of the block. The entire block is heated, and because physics dictates that you transfer heat evenly throughout a surface, the entire block is essentially the same temperature, which we saw there in the previous chart. So doing those individual well monitorings really doesn't tell you a lot about it. It's in my view, it is a pointless exercise because you're not all of a sudden going to find one well that is significantly off temperature where you just can't use that well, but you can use all the other ones around it. It is possible that your heater mat can begin to fail at some point in its life. It is an electronic, it's got wires in there to heat, and as with all electronic items, it will eventually fail. But what that means is that it will just take longer to get to a temperature, or it may not ever be able to reach. If you set it, usually what happens is we'll get phone calls, somebody's trying to heat their block to 115, and it will never register above 75, and it just doesn't have the mat inside has lost power to get any higher than that, and so the entire block will not be at temperature, not just one spot. So if you would like, you may try to convince your auditors or your QA officers that checking every single well on a hot block is less productive, and just monitoring the corners to make sure you've got make sure that it's heated out to the edge is sufficient, and then as long as you check that you're at temperature in one spot, then the rest of it will be fine, and you can work on monitoring from there. All right, I need to speed up a little bit. TKNs, very similar to digestion, metals digestions. You're heating, you've got samples in tubes, you heat them in a block, and they get hot, and fun things happen. So here again is excerpts from the method. Place your tubes preheated to 160, maintain temperature for an hour. Reset temperature to 380, continue to heat for 1.5 hours. This one's slightly differently worded in that it does not actually tell you to heat the samples to these temperatures. It asks you to heat the block to these temperatures. There's a few reasons for that. The first one is to understand the purpose of each of those temperatures and what's happening at those steps. Your initial temperature of 160 degrees is to evaporate water out of your sample so that your actual chemical reaction can happen later. And so for an hour, you're boiling at 160 degrees, and you're removing water and you're lowering your volume down. 380 degrees is where the actual chemical reaction happens to break down all your nitrogen compounds and get your oxidation reduction reaction going to make everything into ammonia. And again, it asks for the block to be set to 380 degrees. Now, I've had people call and ask, how are they supposed to verify that the block temperature truly is 380 degrees? There is not a good way to do that. I think I've got some examples later talking about how the temperature of an object cannot exceed its boiling point. And it's really hard to find a liquid that is still a liquid at 380 degrees Celsius and is still something that you can use a regular thermometer in to actually measure the temperature. Concentrated sulfuric acid will work, but that's a problem because then you're trying to take the temperature of boiling sulfuric acid, which is not an easy thing to do. You could try putting some of your, your sand in a tube and stick a thermometer down in there. I've actually tried that in this, and it never registered 380 degrees. The sand itself still has air pockets in there, and that temperature is high enough that it is driving heat out of those air pockets and heating the air above it, so that you can't get a measurement of 380 degrees using sand. And so I don't have, and even then, we've still got the same temperature transfer rules of going from the metal block through the air around the glass tube, through the glass tube, into the actual material that you've got measured there. So the only really great way to measure the temperature of that block is measuring the block itself directly. Unfortunately, again, I don't know of any good contact thermometers that are set for 380 degrees. So what we've got is the thermocouple that is already drilled into the block and connected to the controller that is telling you the temperature. But we all know that auditors don't like onboard temperature records, because what if they're wrong, and how do you know that they're right? So you have to use some kind of NIST traceable thing there. I don't know anybody that has a NIST traceable thermometer that goes to this range. I'm sure there's some out there, but that's not a common one that you use. So there's all sorts of interesting problems in trying to monitor the TKN equipment. Be aware of those. Be ready to discuss that if you were asked to do so. Distillation. So this is another fun one that I've had some discussions about recently. Here is a snippet from not standard methods, I believe that's EPA 350.1. And it talks about adjusting the pH of the sample, set up your Kjeldal flask. Not very few people use Kjeldal flask anymore. We all use some kind of smaller distillation apparatus, adjuborate buffer. Distill 300 milliliters or smaller, depending on your, you adjust that accordingly, at the rate of 6 to 10 milliliters per minute into a 50 milliliter of 2% boric acid or sulfuric acid, again, depending on your analytical method, and so forth. So we distill the sample. It never tells us what temperature we distill the sample at. I've looked at all the distillation methods that I could find. I looked at phenols, I looked at cyanides, I looked at ammonia, I looked at standard methods, EPA methods, everything that I could find, and none of them actually have a temperature requirement. So then I went and I looked at a few different manufacturers' manuals, operator manuals, and there I actually do see temperatures. Some of them say 130, 135. That's our Simple Dist manual has that in there. Some of them say 160 or 180 degrees. Is there an actual difference? Does their distillation system, do samples in their distillation system only distill at 160 degrees? Does the sample temperature need to be 160 for them and only 130 for us? No, that's not how it works. That's all about getting the sample temperature high enough to make distillation happen. What is distillation? Distillation is simply evaporating a lower boiling substance from a higher boiling substance. So what you need to do is raise the temperature of your sample to boiling. And as long as your sample is boiling, you are distilling. So there is no actual temperature requirement for distillations. I've had that discussion with some people recently. Physics doesn't allow a liquid to be a higher temperature than its boiling point. I may have that written down at some other point in the presentation here. But if you have water, pure water, then pure water cannot get higher than 100 degrees Celsius because all of the heat energy that would normally raise the temperature is now going into vaporizing that temperature and going through a state change. If you've ever had the unfortunate occurrence of your analyst coming and telling you that they're monitoring the temperature and no matter how high they set their block, it never reads above 100 degrees, that's why, because they're measuring water in a block and the water's boiling at 100 and it will never get any higher than that. That's why you sometimes have to use oil to get the readings of something at a higher than boiling point. Incubators. So all those previous examples, we're talking about single sample temperatures and getting an object to go to a certain temperature. Now we're going to talk about environment temperatures. So incubators, I've got a couple of snippets from a few microbiology tests, or excuse me, BOD and microbiology. Although some people might argue that BOD is a microbiology test, but that's again another subject for discussion. So in this one, these are the ones where they give us the ranges. BOD says incubate at 20 degrees Celsius plus or minus 1 degree Celsius. This is the modified MTEC. So the MTEC method talks about incubating your temperature, your samples at 35 plus or minus 0.5 degrees Celsius and that's for 2 hours, and there's some more incubation after that. So in these, we are using an actual enclosed object, an incubator, as you can see in the images, that needs to have the entire temperature inside at a certain temperature within a certain range. And there, so you've got your heating elements around the air, and so you are actually heating the air inside that container to a certain temperature, and then when you place your sample in there, whether it be your BOD bottle or your why am I blanking on the dish? Your microbiology sample, with your filter in it there, or possibly the sample bottle if you're using some of the liquid incubation methods. You're counting on the air inside the oven or incubator to be at the proper temperature, and then bring the object that you have put inside there up to that temperature as well. So here, we want the actual incubator temperature and the sample temperature to be the same. And again, most of the time, you've got your temperature readouts on the outside of your incubator, but we can't use those as the official reading because they're from those untrustworthy manufacturers, and who knows how they measure temperature. So everybody's got their own NIST traceable or NIST calibrated thermometers inside their incubators, also recording the temperature, and those are the ones that you read. Some other interesting things to talk about when you've got your NIST traceable thermometers or your NIST calibrated thermometers is that a lot of times you should have an actual correction factor labeled on that thermometer. In the lab where I worked, we had some little tabs that were attached onto the top of the thermometer with a plus or a minus temperature to indicate how far off it was in relation to the actual NIST thermometer. And so you would look at that temperature, read what was indicated on the thermometer, and then you would add or subtract the correction factor to get the actual true temperature reading of that incubator and of that thermometer. Other similar styles: TDS, TSS, TS, your solids analyses. So there, the first snippet is part of total solids and part of total dissolved solids, where it talks about evaporating to dryness. The middle section is out of total dissolved solids. Is after you've evaporated to dryness, you put it in the oven for at least an hour at 180 plus or minus 2. Or for suspended solids, you dry your filter at 103 to 105 in an oven. So here again, we've got some parts that talk about specific temperatures and some parts that don't. For the longest time, I operated under the assumption that dissolved solids had to go in your oven with your TSS sample set at 104 degrees Celsius to evaporate your water. And then after that, they went to the 180 oven. It wasn't until later when I actually read the method and started thinking about it to understand it, that all it really asks you to do is to evaporate the sample. It does talk specifically about not setting it so high that your sample will splatter and that you will lose something while it is boiling. Total solids specifically says to avoid boiling. I think dissolved solid also says to avoid boiling. But yeah, so you can evaporate the sample however you wish. There's no specific temperature requirement for doing that. The actual temperature requirement only comes into play for total solids. It does tell you to, once it's evaporated, to put it at 104 plus or minus 1, and then the 180 for TDS, and then again 103 to 105. Why they don't say 104 plus or minus 1 there, I don't know, but consistency's sake. So that's that's talking about your temperatures for your various gravimetric things. I didn't put it in here, but oil and grease is another one that talks about that has a temperature mentioned in the solvent evaporation stage, and it talks about I believe previously it mentioned 65 degrees Celsius, which does just fine. But as everybody knows who's worked with hexane, hexane evaporates at room temperature. You can just leave it on a counter and it will evaporate all by itself. So it doesn't have to necessarily go up to 65 to evaporate it. That's just for a speed of use. I found best results when I've actually got my temperature set down lower, around 30 or 35, because then I don't accidentally overshoot that evaporation and then start burning off my residue once the hexane all disappears. So there's lots of wiggle room once you understand what the actual temperature requirement asks for, and if it's a requirement or a suggestion or just a practice that you've always done and never really considered. All right, so that is the end of my presentation, and we've got 15-ish minutes or so with to answer some questions if we've got. Apparently Carlos did appreciate my joke. Thank you, Carlos. Thank you for your response on that. All right, so we've got a question from Maria asking about, could you fill a vial with glass beads, insert a thermometer into the vial, place in a hot block well for temperature monitoring? Possibly. So again, that gets into the same type of situation I talked about with the sand and the TKN unit. Your glass beads, even though they may look like, depending on the size of the beads, they may look like they're nice and compact, you do end up with air in that inside that vial around the glass beads. And so you do lose some heat through the air pockets in between the glass beads being heated. It can work usually on metals digestions. You've got a low enough temperature that it's not quite as fast of the temperature going out to heat other things, to heat the outside air, so there's not as much of a gradient. You would really just have to evaluate it for your particular samples to see how well it functions for you. That, does it give you results that you expect, and does it work out? Yes, Petri dish. Thank you. I appreciate that. I don't know why I could not come up with the word Petri dish. Yeah, thanks on that. All right. So that's really the only question I've gotten about glass beads in there. Oh, there we go. COD temperature requirements specifically. Okay, so I don't have the COD method in front of me, so I don't know I'm not sure the exact wording, but 150 degrees is what I remember from when I've done it. I do not know if it has been given, if the method itself gives a temperature range for that. I think it just does 150 degrees, and I don't think it gives any wiggle room by saying approximately or about. So I know it does not say 150.0 degrees. So you can, you definitely can use rounding if your temperature is, if your thermometer is, sensitive enough that it's doing half degrees at that range. Most thermometers don't do portions of degrees when you get that high. Most of them are just in single degree increments at around that level. So if I remember correctly, the lab where I worked, we had an internal requirement of ±2, I believe, and our reasoning there was that 150 is close to 180, so if they can expect accuracy of ±2 on TDS, then they can probably expect accuracy of ±2 on COD as well. And I do not recall ever being challenged on that by any assessors or auditors. Now, that's not to say that they wouldn't have if they looked at it close enough, but either no one looked at it and thought anything about it, or no one had an issue with it. So that is my understanding of the COD temperature requirements. I do know that I have seen some manufacturers talk about 145 or 148 degrees, and that's manufacturers of specific COD vials. I don't know the general, how that's viewed. I know a lot of times manufacturers' instructions can be given precedence over some things, but I think temperature requirements stated in methods are kind of absolute. So I think that that does have to be set there. All right, let's see here. Ooh, good. Okay, questions are coming in. All right, any idea on the regulatory position on electronic versus liquid thermometers? Again, I've been out of the lab for 7-ish years now. While I was there, my understanding was that the liquid in glass thermometers were gospel, and that the electronic ones were not. I think that position is changing, but I do not have any documentation from anyone in particular that says yes. So that would have to be something that you would need to, if someone has said something to the contrary, that would definitely need to be cleared up with anybody who would be assessing your temperature requirements. So that's, I think it's going towards more acceptance of those. And again, they have to be traceable back to NIST in any case, but a lot of them are becoming so. So it's something worth asking about. Where in a BOD incubator do you take the temperature? High, medium, low? So with that, again, my understanding is there's no specific guidance other than kind of a general feel for the size of your incubator. We had incubators that were the size of your standard, kitchen refrigerators, about 6 feet tall or so, and we did have different ranges in those incubators where we were taking temperatures. The same thing for your microbiology incubators also. We had some circulating water baths that we just took the temperature of the water, but then we also had a larger air incubator that we needed to take the temperature in various levels of it. And that's just because of the possibility that, obviously if, warm air rises, and so it could theoretically be warmer at the top than at the bottom. If you have a circulating incubator, a convection incubator, you may be able to argue that the one temperature is the same all around because you've got the fan moving the air around and keeping it mixed, but they may ask you to take the temperature at various levels simultaneously. Maria says we run a standard with COD samples to make sure we have complete digestion. That I have seen that used, yes. So that can be something that you can use to show that your temperature is correct. How often should digital thermometers be verified? My understanding is minimum yearly, possibly quarterly. I don't remember the actual requirements, and there may be different program areas with different requirements. DoD may say one thing, T&I may say another thing. So you would need check the program requirements, your quality manual or your quality plan or whatever it is there, the standards for that program area, to see what they say for your verification frequency. Interested in connecting fridges, incubators, and other thermometers to an auto recording system for some sort of daily monitoring. So if you want to do that, so the Traceable Life that I was talking about, that is possible to do. You can have those electronic thermometers inserted in all your various places that you need to take temperatures on a regular basis, and they would all report into one app. And you can pull up reports for that. You can have alerts set to let you know if something, if a particular area is out of control or getting close to out of control. Again, that would have to be something. Make sure that your regulators are okay with that. I believe if you can show that you are tracing back to NIST with everything and you have calibration checks at the proper frequency, that you should be able to make that happen. Auditors are generally becoming more accepting of technology, but they work slower than the rest of us want to work. So it may take a little bit of time. It may take some convincing on your part. They may want to see security records or something to make sure that records can't be falsified. Data is going to be accurate and is going to be reliable for what they need to report. So you may need to show something for them to be able to accept that. And that is something that with our product we can help with. We've got some information that we can send out, some things that we can help with to get all that going. Once a correction factor is determined, does the thermometer need to be re-verified at the adjusted temperature with the correction factor applied? So the way I understand the question, I don't think so. The way our lab did it was we just had the official NIST thermometer and the in-use thermometer side by side in the same environment, the same liquid, the same whatever. And so you would take the reading of your NIST thermometer, you would take the reading of your active thermometer, you would compare the two, and then you would just say this one is +1 or -0.2 or whatever, and you would just attach that correction factor to the thermometer so that anybody using it knows to add the appropriate correction factor when they're taking a temperature reading and just go from there. So I don't think you have to redo anything if you're doing them side by side to show what they are. Sample storage fridge that exceeds its requirements by a few degrees C. That's an interesting question. A specific example you say, such as soil for semi-volatiles. So I do know the best appropriate correlation that I've got there, where I've got some specific guidance, is in microbiology, because as you're adding room temperature petri dishes or sample bottles into your incubator, just opening the incubator, adding things in, you're going to change that temperature. Usually it's going to drop below your actual required temperature, and then the controller has to, add a little bit more heat to bring things up, and so it's going to creep up a little higher than your temperature, and then it's going to drop back down and get to the right thing. And so what they told us was that I think we had 30 minutes that we could not add samples or have the door open any longer than necessary, where it would take more than 30 minutes for the samples, for the incubator itself to get back to the proper temperature. So in this case, I presume that in this situation, you're opening the refrigerator to put samples in or take samples out or whatever, and maybe there's a lot of them, you have to do a lot of things at one time, and it's open long enough that the temperature goes out of its specification. My understanding for that particular case is that if it gets back into temperature within a reasonable amount of time, and again, this is my interpretation, I would expect 30 minutes to be acceptable in this case as well, that there doesn't need to necessarily be any data flagging that goes on with that. If you have a temperature failure where maybe the entire incubator doesn't fail, but it's losing efficiency, the refrigerant needs to be recharged or something, and it can't actually hold temperature at the correct level for an extended period of time, that is when you definitely have to qualify things, and there's going to be some possible violations with samples that were in that refrigerator. Again, my interpretation as far as I understand the question and how things go. Large incubator, and you have top shelf and bottom shelf, adjusting the total incubator for both thermometers so that both are 35 plus or minus a half. So you say that both are in range with the correction factors. What you have to remember is that if one thermometer reads 35.5, but it has a correction factor of -0.5, the other thermometer reads 34.5, but it has a correction factor of +0.5, then even though those thermometers physically read 1 degree apart, the correction factor applied to them makes them the same. And so they are reading the same because you apply the correction factor after you look at the actual reading of the thermometer. Now, if you are applying your correction factor and you still have, in a large incubator, the top different from the bottom, that's when you need to actually evaluate the efficiency of your incubator itself. Is it an old incubator and maybe some of the insulation or the seals are not good anymore, and so it's gotten out of spec? Maybe the heating element inside that incubator or the controller that sends information to the heating element to turn on or off, maybe it doesn't respond as fine-tuned or as quickly as it should, and so you get differences in temperature. The hot air is going to rise, and so the hot top is going to be hotter than the bottom. You've actually, the larger incubators, you may need to just go ahead and invest in a convection oven or a convection incubator so that the entire incubator has a better chance to distribute heat throughout it at an equal rate. So that's, in that type of instance, you probably should evaluate the incubator itself and see that, see if you can get a better one. Crystal, is there anywhere you're aware of that says how long an incubator is allowed to be out of temperature? So I talked a little bit about that in the previous question. I know specifically in the state of South Carolina for microbiology, they said the 30 minutes was an acceptable time to creep out of range because you're putting things in or have the door open, and then to get back into range. I don't know if that is the same for everyone everywhere. My experience has always been that if you put it in writing in your SOP and then adhere to that, usually you're going to be okay as long as it sounds reasonable. I don't think you'll be able to say you can be out of hold for a day or out of spec for a day before it gets back in range. But if you have something reasonable, 30 minutes, 45 minutes, maybe you can push it to an hour, I don't know. But if you put something reasonable in writing in your SOP and then follow it, that you're rarely going to encounter any problems. NELAC, liquid filled, calibrate at least once a year. The rest, digital, thermocouples, accelerators, etc., calibrated quarterly. Thank you, Wanda. So there we go. Wanda has some references from NELAC, TNI about times of calibrations and to check it. Let's see here. Metals digestions block, do verifications in the corners and the so when I was talking about the metals block, verifying temperatures on a digestion block, I would do the corners and the center. Now the center of those blocks are square, and so there's no actual one spot in the center. There's 4 spots that are around the center. I think you could pick any one of those 4 spots around the physical center of the block, and then each of the corners to do your temperature verifications, and you can use that to show that your entire block is within spec. That's my interpretation, and that's what makes sense physically with how physics works. Should infrared thermometers be calibrated more often than every 6 months? According to NELAC, they are not a liquid in gas or in glass, so yes, they should be done quarterly. Best practice for monitoring a sample storage fridge over the weekend. Well, old school is you have somebody physically come in every day and take your temperature readings at least, I think we had 4 hours apart, I think was what we were asked to do. I don't remember the exact thing. So the best way that you know it's actually going to be done to adhere to recommendations is to have a physical person walk in at certain times and write the temperature down. This is another case where getting electronic monitoring may work for you. It's definitely something I would shoot for. Last question, because I'm a minute over. How do you get a good temperature on a multi-furnace at 550 degrees? Do I have a thermometer that goes up that high? That's the million-dollar question, Thomas. I don't know, and no, we do not. Muffle furnaces are ridiculous in their temperature settings. I've luckily never had anyone ask for temperature verifications on a muffle furnace. I hope that you are not unfortunate to have someone ask that, because I don't have any suggestions on that. Sorry about that, but that's the best I got. And we are now out of time. Thank you everyone for being here. Appreciate it. Hopefully you've learned something. Again, these are all my thoughts and opinions. Please pass everything by your regulators before you start doing it. Saying David said so is usually not going to fly. Thanks again. Look for the invite for next month on our topic, on our webinar for September. If you've got an idea, let us know. And everybody have a good day. Bye.